Hello everyone. In previous videos, we highlighted GNSS as a key enabler for the smart cockpit. Today, I'll introduce Unicore's GNSS solutions for automated driving. This presentation is divided into 4 parts. First, we'll analyze the automated driving market based on different levels of driving automation. Second, we'll examine the mainstream demands shaping today's solutions. Third, we'll see our product solutions tailored to various needs. Finally, we'll share our future vision for safety-critical system architectures. In terms of the automated driving market, we categorize it into 3 main segments based on the SAE standard of automation levels. Level 2.5 plus, partial driving automation, is an extension of L2. It represents sophisticated driver assistance. The system is able to control steering, acceleration, and braking in scenarios like highways or urban environments, but the driver must remain engaged and supervised continuously. In application, you see this as NOA, Navigate on Autopilot, for highways and city roads. Highway NOA primarily assists with lane changes, entering or exiting ramps, adaptive cruise control, and speed control. Urban NOA assists with various corner cases in city driving, including lane changes, navigating intersections, and traffic jam pilot. Level 3 conditional driving automation marks a fundamental leap. The system can perform all driving tasks in certain predefined scenarios. The driver can disengage from monitoring but must be ready to take over when requested. The revolutionary aspect is a shift in liability from the driver to the manufacturer. This places higher demands on sensor safety, anti-jamming, and anti-spoofing capabilities. Finally, L4 and L5, the realm of fully driverless operation. L4 refers to high automation within a specific operational design domain where no human intervention is required. L5 is the ultimate goal of full automation, capable of handling all driving tasks under all conditions. A typical application of the L4 and L5 driving automation is robotaxi. Turning to market demands, we see automated driving evolving along 2 distinct paths. The entry-level path, which starts from a cost-effectiveness threshold and focuses on basic driver assistance features, is taking a bottom-up approach to build upward compatibility. It relies on algorithm advances to add features. GNSS is used for SD map matching, delivering 70 to 100 centimeters accuracy, 5 to 10 Hz output rate, and 100 nanoseconds time synchronization. The premium path, which offers advanced features and focuses on superior comfort, handling, and seamless performance, is following a top-down approach to pursue downward compatibility. The strategy is to reduce hardware and enhance algorithms. Here, GNSS matches HD map, delivering 10 to 20 centimeters accuracy, 10 Hz output rate, and 50 nanoseconds time synchronization. Based on the above evolution path, the GNSS requirement landscape is summarized as follows. Dual frequency single point positioning serves as the entry-level requirement, suitable for basic driving automation. Dual frequency RTK serves as the performance enhancement layer, crucial for solving corner cases and improving reliability. Triple frequency RTK serves as the safety and redundancy layer. Its primary value is not in outperforming dual frequency on pure accuracy, but in providing system robustness to meet stringent functional safety standards. Now let's talk about Unicore's strength. First, chip cloud integration. Unicore is a subsidiary of BD Star, which also includes TruePoint, a specialist in high-precision cloud services. This makes us one of the very few companies capable of delivering a cheap cloud integrated solution. This approach simplifies the integration process, reduces costs, and enables faster troubleshooting for customers. Next, customization. As many OEMs and Tier 1 suppliers develop their own algorithms, we adapt by offering tailored protocol outputs that match their specific needs. This flexible, client-centric approach empowers our partners' unique innovation path. Next, rapid response. With our sales and FAE teams distributed worldwide, we provide localized, on-demand support for testing, integration, and issue resolution, always ready to assist at a moment's notice. Next, diverse solutions. Our product portfolio is designed for versatility. They are compatible with high, mid, and low-tier automated driving architectures, support both on-chip and off-chip algorithm configurations, and can be paired with IMUs of various performance grades to fit diverse system designs. Next, reliability. Our GNSS modules used in automated driving operate reliably in temperatures from -40 degrees Celsius to 105 degrees Celsius and are AEC-Q 104 certified. This guarantees stable performance under the most demanding automotive conditions. Next, versatility. Our testing has covered diverse road environments across China and overseas regions, like Germany, Japan, and Northern Europe. This ensures our products are proven in a wide range of corner cases. Next, functional safety. Safety is engineered into our modules. We conduct FMEDA assessments, ensure protection level safety outputs, and implement software redundancy, all to maximize system safety for ADAS and automated driving applications. Next, supply stability. With over a decade of experience in automotive navigation supply, we guarantee long-term stability and reliability across the supply chain, providing our customers with confidence in mass production and lifecycle support. Finally, demand matching. We deliver exactly what the customer requires. Unicore offers 4 dedicated chip platforms for the automated driving market. Our product portfolio is designed to meet the diverse GNSS needs across different clients, systems, and sensor fusion algorithms, ensuring our partners receive optimal value without overpaying. Now let's see Unicore's product portfolio for automated driving. Leading our portfolio is the UM1080A, built on our top-tier Nebula series platform, delivering ultimate performance for the most demanding applications. It supports triple frequency signals, namely L1, L2, and L5, providing superior resilience in challenging environments like urban canyons, and achieves centimeter-level precision under open sky. Customers can leverage our integrated RTK engine or utilize the raw observations to develop their own algorithms. With a standard footprint of 22 mm x 17 mm and a typical power consumption of 450 mW, it's the ideal choice for L2 plus driving automation. The UM681A is offered for scenarios where GNSS signals are briefly interrupted. This module combines dual frequency, that is L1 and L5 GNSS, with a built-in IMU to output RTK and DR integrated solution. This ensures continuous high accuracy positioning in short tunnels, underground parking garages, and under overpasses. It also outputs configurable raw IMU data at 50 Hz or 100 Hz. It's in mass production for V2X demonstrations and is an excellent fit for T-boxes or cockpit systems requiring lane-level navigation. The UM680A represents the mainstream demand in the ADAS market. This module provides dual frequency, L1 and L5, RTK positioning, and can also output route observations. It achieves an optimal balance between performance, functionality, power consumption, and cost. It's already in mass production for leading OEMs, deployed in ADAS domain controllers and P boxes. The UM671A is tailored for automotive-grade V2X, offering a configurable dual frequency, L1 plus L5 or L1 plus L2, and DR fusion solution. This dual frequency design can be seen in several Japanese, Korean, and North American OEMs in their vehicle navigation systems. Finally, we have the UM670A module, which provides dual frequency single point positioning with route data output. It features remarkably low power consumption of about 150 milliwatts and is a cost-effective solution, widely used in ADAS and P-box applications. To summarize, Unicore provides three categories of products to match your exact needs. The RTK output class, including the UM1080A and UM680A, serves as the high-precision foundation for advanced navigation systems. The route observation class, represented by the UM670A, prioritizes flexibility by providing direct access to route observation data. Finally, the DR Fusion output class, featuring the UM681A and UM671A, ensures resilient and continuous positioning even in challenging environments such as tunnels or urban canyons. Now let's turn to the deployment architectures for automated driving. There are mainly two schemes for integrating our products. The first scheme, shown on the left, is the GNSS domain controller integration. Here, all positioning-related components, the GNSS module, the RTK engine, and the high-precision DR algorithm, are integrated directly into the ADS domain controller. The blue section highlights what Unicore and TruePoint provide, including the GNSS modules, RTK algorithms, DR algorithms, and cloud-based data services. The key advantage of this scheme is the ultra-low latency. By keeping hardware and software within the same domain, it delivers the fastest and most precise location data to the multi-sensor fusion system. In this setup, the ADS domain controller can share its high-precision positioning data with the cockpit. Meanwhile, the cockpit usually contains a communication and navigation combo chip. This results in two independent GNSS sources for redundancy. The scheme on the right represents an emerging trend, the T-box-based architecture. This scheme integrates the GNSS module and all positioning algorithms into the T-box. The T-box then broadcasts the high-precision position to both the ADS and cockpit domains. The major benefit is the cost-effectiveness and hardware simplification, as the entire vehicle uses a single GNSS module. However, a consideration is the potential for increased latency due to the cross-domain transmission of the positioning data. Next, let's examine the real-world performance of our chip cloud integrated solution, combining Unicore's GNSS modules, RTK algorithms, high-precision DR algorithms, and TruePoint's high-precision cloud services. The first test was conducted in an urban NOA scenario at the China World Trade Center in Beijing. This area is a challenging GNSS environment with overpasses, heavy multipath interference, and tree shades. The test covered 25 kilometers in 55 minutes at an average speed of 27 kilometers per hour. During the run, our chip cloud system achieved an RTK fix rate of approximately 80%, with DR covering 20%. The horizontal positioning error of 2 sigma was consistently within 1 meter. The second test was performed in a signal-degraded environment under a continuous overpass on Beijing Fushi Road. Over a 5.6-kilometer route lasting 10 minutes, our chip cloud system maintained positioning with DR engaged for 55% of the time and achieved an RTK fix rate of around 45%. The 2 sigma horizontal error maintained at approximately 1.2 meters. In the third test, we selected the Chongqing Expressway with continuous tunnels, focusing on a key safety parameter, that is, how quickly the system recovers an RTK fix after exiting a tunnel. Given that vehicles often encounter ramps after exiting tunnels, it could be hazardous if the position fix was delayed or inaccurate. To address this, we measured the reconvergence time to RTK fix. Over 10 runs, the system demonstrated rapid recovery, with an average of around 4 seconds to re-establish an RTK fix, thereby ensuring safety during these critical transitions. The following chart demonstrates the capability of our high-precision DR algorithm. Across 39 instances of signal loss in multi-tunnel scenarios, the error rate remained below 0.2%. Notably, even during one extended outage over 10,000 meters, the error rate was only 0.135%, showcasing exceptional positioning accuracy. This table summarizes the overall chip cloud system performance. In severely obstructed and multipath environments, the horizontal position error remains around 1 meter. Furthermore, the DR horizontal position drift after loss of lock remains within 0.2% over 2 kilometers. Looking ahead to the imminent rollout of L3 automated driving, where liability shifts from driver to system, functional safety is no longer optional but a fundamental requirement. In this context, true GNSS functional safety must be a system-level chip cloud integrated endeavor. Relying solely on an ISO-B certified chip or module is insufficient to address the potential GNSS failures in a complex driving environment. To this end, Unicore and TruePoint are jointly developing a systematic functional safety solution. This architecture integrates an ISO-B certified chip designed with built-in safety mechanisms, a safe positioning engine designed for SOTIF, high-precision cloud services compliant with IEC 61508, featuring integrity output. Together, these elements form a complete system-level solution to meet the rigorous demands of true L3 autonomy. To conclude, Unicore's GNSS product strategy for the automotive market is comprehensive. For standard cockpits, we recommend the single-band GNSS modules, UM760A and UM761A, and the dual-band GNSS module, UM620A. For advanced cockpits, we recommend the dual-band GNSS plus DR module, UM621A. For mainstream driving automation, we recommend the dual-band GNSS modules with raw data output, UM670A and UM671A. For advanced driving automation, we recommend the dual-band RTK module, UM680A, the RTK plus DR module, UM681A, and the tri-band high-precision module, UM1080A. Finally, we are committed to supporting all our clients through efficient localized service, extensive service channels, and guaranteed after-sales support to ensure every client receives stable, convenient, and rapid assistance. That's all of this presentation. If you have any questions, feel free to leave your comments below. You can also visit our website for more information. Thanks for watching. I'll see you next time. Bye!